All right, well, thank you for the invitation to speak here. So yeah, today I'm going to talk about recent work. It's not on the archive yet, but hopefully it should be on the archive in the next week or two. And this is work on initial degenerations of flag varieties. And this is joint with Jorge Alberto Arte. Okay, so the first thing I want to do is sort of give the general setup for initial degenerations of just any subvariety of an algebraic torus, and discuss some motivation why one might be interested in actually understanding the initial degenerations of such a space. Okay. Right, so the general setup is the following. You start with some subvariety X of some torus T. Say this is isomorphic to C star to the N, right? So just, so really it will be important that we're working over characteristic zero algebraically closed field. So let's just, for this whole talk, we'll use the complex numbers. And maybe I'll comment why later, why this is important. It amounts to the fact that we'll be dealing with matroids and realizability. Okay. Right, so this is some closed subvariety. Then you, to such an object, you can form its tropicalization. This is hopefully familiar in for this this workshop, right? But just as a reminder, the tropicalization of X, you can define this to be the set of points W and R to the N, such that right, W is the coordinate-wise valuation of some X, which is some L valued point of X, where L is some valued field extension of C. Okay. And so if you're given such a W in the tropicalization, you can form the initial degeneration of X with respect to this W. So this is denoted by in WX, right? So this is the initial degeneration, or maybe W initial degeneration. That's probably not visible, but W initial degeneration of X. And I'm like, it's a little bit cumbersome to write this out in details, right? But X is, it's defined by some ideal inside the Laurent polynomial ring and then variables. And so using Grobner theory, you can, this vector W induces a term order, so you can you can take initial forms of the elements in your ideal, and then you take the ideal generated by those initial forms. Right, so maybe a succinct way of summarizing this is it's the space cut out by the W initial forms of elements of the ideal of X. Okay. So now, I guess I didn't plan this super well. I'll try to work down here for a bit. Okay, so now why study initial degenerations? Why are they interesting? Right, so there are two motivations that I find interesting. So the first motivation comes from this notion of tropical compactifications. Right, and this notion was introduced by Topolov. About 15 years ago or so. And so the rough idea is the following, right? If you have such a tropical compactification of X, let's call it X bar, then the strata of X bar essentially correspond to the initial degenerations of X, right? So roughly speaking, they're, right, the strata of X bar are parameterized by the cones of the tropicalization. And so the stratum of X bar corresponding to a cone that contains W in its relative interior is isomorphic to the initial degeneration of X up to a torus factor. So you have to multiply, you know, this side by an appropriate torus, and then you get something that's well, not non-canonically isomorphic to this initial degeneration. So in particular, right, the strata are smooth if and only if the initial degenerations are smooth, right? The strata are connected or irreducible if and only if the same thing holds for the initial degenerations. Right, and so this is nice because this is some, you know, initially it's some esoteric geometric construction, and this allows you to work computationally. Right, so this correspondence, I believe, is due to Helm and Katz. I think it's, their paper was published 2013. It's not the main result of their paper, but it just appears here. And so sort of in this family of ideas of tropical compactifications, there's this notion called being shun. Right, and one equivalent way of phrasing whether a close subvariety of an algebraic torus is shun is by requiring that the initial degenerations are all smooth. Okay, and so for this class of varieties, notions from birational geometry admit tropical characterizations. So for example, this notion called log minimality or ampleness of the log canonical divisor, right? These all have tropical characterizations. Right, so this is work in this paper by Heikenkiel and Topolov. Can the camera see if I write down here? Cool. All right, so this is due to Heikenkiel and Topolov. Okay. And then this will be important for many of the applications that I'm particularly interested in. And so the second application of understanding initial degenerations are connections to the analytification. Of X. Right, so one example is that, okay, if the initial degenerations of X are all irreducible, then the tropicalization of X is what's called faithful. Meaning that the tropicalization map from the analytification of your variety into the tropicalization admits a continuous section. So this is due to Gubler, Rabinoff, and Werner. And then as I asked Martin earlier today, so I hope I'm representing Martin correctly here, and also correct me if I'm wrong, right? If the initial degenerations are also smooth, so if they're smooth, both smooth and irreducible, then the tropicalization map is actually a homotopy equivalence from analytification to the tropicalization. This seems to be a folk theorem that all the cool people know. It's just apparently not written down, so I can't cite it. Okay. Cool. So the focus today, of course, will be understanding the initial degenerations of a particular class of varieties called the flag variety. Okay. Okay, so strictly speaking, we'll be working with the type A flag varieties. So these will be generalization. This will be the generalization of your ordinary Grassmannian, right? So the input data for our flag variety will be some increasing sequence, which we'll call R. Right, so this is some increasing sequence of natural numbers, and they're all less than n. Right, so we have some larger integer n. And then the flag variety right, this is as a set, it's the set of all sequences of subspaces, F1 through up to Fs, such that, right, the dimension of Fi equals Ri. Right, so as a special case, you have your ordinary Grassmannian, the space of all subspaces of your n-dimensional. Oh, I forgot to include, right? These are all linear subspaces of C to the n. Right, so as a special case, you have the Grassmannian, where R just has one constituent. And this is the next natural generalization of that. Right, okay, so this describes what the flag variety is as a set. And of course it is, you know, as the name suggests, it is an actual variety. Right, so you can embed, you can think of the, here it is. You can think of each of these subspaces individually. And when you do that, that sort of allows you to realize the flag variety as a subvariety of this product of Grassmannians. Right, and then with each Grassmannian, you can embed via the Plucker embedding into projective space. Should be a P. Right, and so this realizes the flag variety as a multi-projective variety. And this is the embedding we actually want to take throughout, right? So remember, it's somewhat implicit in the description over here, but the tropicalization of your variety, it's something that doesn't depend on the variety itself, it depends on the variety together with an embedding. So the embedding that we're using is this guy. Right, so inside this guy, you have a dense torus. Right, it's just taken by, you know, having all of the coordinates not equal to 0. And so this gives us this open flag variety. Right, this is just the intersection of, this is the part of the flag variety that meets the dense torus. Right, so very concretely, it's the flag variety, the points in the flag variety, all of whose Plücker coordinates are not equal to 0. And so the sort of goal of our project was to understand the initial degenerations of this flag variety. And what we do is we're going to relate them to what these objects called evaluated flag matroids. Right, and the whole motivation for trying to better understand these initial degenerations and put this in a different language will be to come up with ways of actually testing or figuring out when these initial degenerations are smooth and irreducible. So we could, send it through some of this machinery and get other cool results. Okay. So I'm assuming maybe a new vocab word. So I'm going to spend the next section sort of giving a rough outline as to what these objects are, these evaluated flag matroids. Okay. All right, so we'll title this next section just flag matroids. Right, and the description is going to go through, or by analogy, with ordinary matroids. Right, so the nice thing about what we need about flag matroids for this talk is we actually only need to know about realizable flag matroids. And these are substantially easier to define, although perhaps less illuminating than the definition coming from abstract matroid theory.
There's a question in the chat.
Yeah.
Bruce, do you want to ask yourself or should I just read out?
Oh yeah, great. So hey Dan, if we took the complete flag variety, so no gaps, then is the answer to these initial degeneration questions easier in that case? Is that like a better behaved case?
So in that case, we have nice parameterizations of the flag matroid strata. It's so weird trying to talk to you because I don't know where to look. Here, I guess right here.
Yeah, that's
It's like talking to the ether.
that's usually what it's like talking to me though. So
I mean, yeah. So I think one thing that makes it easier is less from the initial degeneration point of view, but more from the parameterizing these matroid strata. And there's a good way of parameterizing them in the complete flag variety case, and maybe there's a nice way of doing it for the non-complete flags.
But it's not like the answer is they're always smooth and irreducible or they're always tori or something.
Yeah, I don't think that's the case. I don't have a proof of this.
Okay, cool. Thanks.
Suspicion is no.
Cool.
Okay. Right. So now, let me give an introduction to flag matroids. Right. So for an ordinary matroid, let me just describe what happens in the realizable case. Right. So if you have a subspace of dimension R inside of C to the n, then I'm gonna denote matroids by Q. You can form the matroid, and the perspective I'll take is from the point of view of bases. So you can define this to be the set of lambda in the n element subset or the R element subsets of n, such that the lambda Plücker coordinate of F is not equal to 0. Right? There are many, many different ways of defining a matroid in the realizable case. This is just one of them. It's sort of well suited for our purposes. Okay, so if you're familiar with matroids, you verify that this is a matroid in the abstract sense, that it satisfies the basis exchange axiom, but whatever. So similarly, right, if you have a sequence, or a flag, I should say, of subspaces, right, then you can form its flag matroid, and it's just going to be the sequence of the matroids corresponding to the constituents. And this satisfies, there is an abstract definition of what a flag matroid is for, you know, arbitrary matroids. And it turns out that when you do have a sequence of subspaces like this, these satisfy the axioms of this abstract flag matroid. If you're familiar with notions for matroid theory, the quick way of saying what this condition is that if you have matroid over here and some matroid over here in the sequence, then the guy lower in the sequence is a quotient of the guy higher in the sequence. Meaning that the flats of the guy in the lower part are contained, the set of flats in the lower part are containing the set of flats of the upper part for each pair. Okay. So now, given matroid Q, there are two pieces of data you can associate to this. One that's more of like an algebraic geometric piece of data, and the other is more combinatorial. So the first piece of data, or the first datum you associate to this Q is the stratum, GRQ. So I guess I didn't throw in this notation, but right, let's say Q is a rank R matroid. Right, then this, so this here is what's called the Finn-Schubert cell or a matroid stratum. And said theoretically, it's just all of the subspaces whose matroid is Q. Right, and you can think of that as some subset of the Grassmann. It turns out to be some locally closed subscheme. Right, so here where we're using the definition of the matroid of a subspace given here. Okay, at the other end, you can associate what's called the matroid polytope to Q. Right, so this is some polytope in R to the n. It's given by the convex hull of the vertices essentially correspond to the bases of Q, right? So it's like the vertices are like the indicator vectors of the bases, essentially. Okay. And so, right, we can now make an analogous definition for flag matroids. You know, we're going to switch these. Right, so if you're given a flag matroid, say Q vector, so this is Q1 through QS. Right, so the one generalization will be pretty obvious in some sense. Right, so above when we had just a single matroid, right, you had some stratum in the Grassmannian, right, the subspaces that realize that matroid. So the analogous construction for flag matroids is a stratum in the flag variety consisting of the flags that realize that flag matroid. The thing that's slightly less obvious is what the polytope should be. And it turns out that the correct generalization of the polytope of a flag matroid is given by the Minkowski sum. Right, but it turns out that, okay, so for us, the important piece of data actually is going to be a little bit more than just the polytope. Rather, we also want to keep track of all of the ways in which lattice points can be formed as sums in the constituents. So really, we're going to want to think of this actually not as a polytope, but as a point configuration. And so let me describe what this looks like in an example. All right. Right, so actually there's going to be a few other notions that I want to talk about, and I'm going to describe them or illustrate them through this running example. Okay. So the example is the following. So here our flag matroid Q vector, this is the uniform 1, 3, and then the uniform 2, 3. Right, so even more concretely, right, the bases of the uniform 1, 3 matroid, these are just 1, 2, 3. And then for the uniform 2, 3 matroid, it's 1, 2, 1, 3, and 2, 3. Right, so here I'm using juxtaposition, not this, so don't read this as 12, but read this as 1, 2. Okay. Right, so the stratum, I'll write this up here. Of this is literally just the open dense part of the complete flag variety of, I guess, rank 1, 2, and one-dimensional subspaces and two-dimensional subspaces in C to the 3. Okay. So now let's look at what the polytope is. Right, so we take the polytope of the uniform 1, 3 matroid, it's just a triangle. And then the polytope of the U2, 3 matroid, which is also just a triangle. Let's label the vertices. So this is something like 1, 2, 3, 1, 2, 1, 3, 2, 3. And so let's take their Minkowski sum. And you get a hexagon. Okay, right. So each of the vertices of this hexagon is some unique combination of these numbers, right? So of these vertices. So this vertex here was can be represented as the sum of the vertex 1 and 1, 2. Right, so similarly over here, this is 1, 1, 3. Down here is like 3, 1, 3, 2, 2, 3. I guess this is 2, 1, 2, and then last but not least, I guess this is 2, 2, 3. Sorry, this is 3, 2, 3. Okay. But we don't have just these 3 points, right? So in the Minkowski sum of polytopes, right, you just take the convex hull, done. But for us, we actually will want to carry the data of the vertices. So we also have, right, a vertex in the center. And this can be formed 3 ways. It can be formed as 1, 2, 3. But it can be formed in 2 other ways. As 2, 1, 3, and then 3, 1, 2. Right, so think of, I'm sort of spreading them out for emphasis, but this is all 1 point. But you should think of it as a point with 3 labels. Okay. So this is what I mean by the point configuration of your flag matroid. Okay. So now let's get into the evaluated part. So I'm going to keep this as a running example over here, but I'll just continue the prose here. Right, so now if you have a vector W in, for example, the tropicalization of the Grassmannian, right, this open part, guess this is more consistent. Then if you, right, so this W, right, you're supposed to think of this as living inside of wedge R to the n, right? So the coordinates, or sorry, that's in the uniform case. This is, oh yeah, I guess I do have the uniform case written here. That's fine. Actually, let me switch this to just the general, the matroid. Right, so the coordinates of such a vector, right, correspond to the vertices of your matroid polytope. So you can use those to lift your matroid, the vertices of your matroid polytope in some orthogonal direction from Rn, right? And so this gives you some new polytope that's kind of bent. And so you look at the lower faces of that and you project that back down. And this gives you what's called a regular subdivision of your polytope. And so the key fact about a point being in the tropical Grassmannian is that all of the polytopes in that regular subdivision are going to be themselves matroid polytopes. Right, so I'm going to write curly Q for the subdivision. This is the regular subdivision induced by W. And the key fact is that this is matroidal. Right, and so this is due to Spire. Okay, so then in a recent paper by Brantner and Zhang, they generalized this to the flag variety. But it's a little bit trickier, right? So, okay, so when you see a Minkowski sum of polytopes or a Minkowski sum of point configurations, and you want to think about subdivisions, right? Like the one concept that should be blaring in your ears is something called the mixed subdivision, right? So it's a particular type of subdivision of your Minkowski sum such that each polytope in your subdivision is a Minkowski sum of faces of your constituent polytopes in your sum. And so so this condition, whatever this is going to be, should pass through mixed subdivisions. Right, so let's say W is, let's write this out as W1 through WS. So this is a point in the tropicalization of the flag variety, but rather this strata corresponding to a flag matroid Q vector. Right, so remember, given our embedding of the flag variety, you should think of this as living inside of R to the Q1 Cartesian product through R to the QS. Okay, so now the points in the Minkowski sum of the point configuration, they're naturally in bijection with the Cartesian product of Q1 through QS. Right, so we actually have this map phi from this space here, Q1 through our QS, to now, right, we want the number of coordinates of this to be in bijection with the Cartesian products of the sets Q1 through QS. And so the candidate is the tensor product of these vector spaces. And so we have this map, and it's defined, let's define this by taking the vector W vector. And this goes to W1 tensor all ones vector in all of the other places. And you just do this for each constituent. So in the next one, we'll have W2 here and all ones everywhere else, and so on. Right, so in general, right, this vector now we can now make sense of this as a lifting function on the points in the Minkowski sum of the point configuration. And so if you lift up all those points given by this function, and then look at the lower hole of this lifted point configuration and project everything back down, you get a regular subdivision. So I'll denote this by fancy Q of vector W. All right, maybe the notation for the talk isn't super great, but.
Is this like another way of like the matrix
Yeah, I wish Jorge was here to answer that. So the way my understanding of this is it's another way of writing down, right? So when you do the regular subdivision induced by this guy, right, it will be the coherent, coherent mixed subdivision of the Minkowski sum of the point configurations with these constituents. And it also has an interpretation in terms of what is it? In terms of these like fiber, this like fiber polytope thing. I'm losing the jargon being in front of everyone here, but there's like there's an analogous notion of like a coherent fibered subdivision. And I don't quite know off the top of my head how to fit the Cayley trick into here, but I'm like positive it's in here somewhere. Okay. And so the key fact is that this subdivision is flag matroidal. Right, given when W vector is in the tropicalization of the flag variety or of this flag stratum. And this was due to Grant and Zhang quite recently. Okay, so maybe to illustrate this concept, let's look at the example. Okay. I stole the red chalk. Here it is. Right, so let's take W vector to be, right, 1, 0, 0 for the first one, right? We need coordinates for each of the coordinates here. And then just 0, 0, 0 for the lifting down here. I'm going to write this in 2 lines. There we go. Right, so basically what this is saying is that in the picture, the way you're supposed to read this is that everywhere there's a 1 in the first place, right? You lift that coordinate up by, height 1, right? So right, this point gets lifted up by 1, this one by 1, and this one by 1. And so this is now some lifted point configuration, and you look at the lower faces. And so when you do that, you get something that looks like this. Right, so when you look at the lower faces and project down, this is, right, you're going to get the outside vertices, of course. But these two are staying at level 0, and this one's going up to height 1. So this one's going to disappear from the regular subdivision of your point configuration. Oh, I didn't draw this the way I wanted to draw. Right, so you're only going to be left with 2 points in the middle. And so now to draw the subdivision, I'm going to sort of separate out all of the pieces. Right, so some of the drawings here are a little redundant. Right, so you get 2 top dimensional faces, the top and the bottom. And then you get this codimension 1 face in the middle. And so you can, so really, I'm sort of not writing it down here for space, but when I'm saying that this is flag matroidal, I'm saying that the point configurations themselves are point configurations of flag matroid. And so you can kind of see how, since we're discarding this point, how, for example, this top polytope is the Minkowski sum of a triangle with a line segment. Same with the bottom polytope. And then the middle is just the Minkowski sum of 2 line segments. And so in each of these cases, each of the polytopes is a flag matroid. Okay. So we're about ready to get to the main theorem. We just have one last ingredient. Right, so far I've just sort of been going definition crazy. And I haven't really stated, well, I guess I have stated some theorems, but just not anything that we've done. But maybe here is a fact that's probably new to us. So here's a key fact. Suppose you have 2 flag matroids, vector P and vector Q, and suppose the polytope of vector P is a face of The polytope of vector Q. Okay, so I guess I'm being a little sloppy, right? We really want to work entirely with point configurations. And with point configurations, you can define face. There is a well-defined notion of the face of a point configuration. So really, it should read the point configuration of this flag matroid as this is a face of this. Then there's a natural morphism from the strata corresponding to Q vector to the stratum corresponding to E vector. Right, obviously you can just, maybe you could just write any old stupid map down, but the point is that there's like some naturally well-defined functorial map or assignment from the face post set of a subdivision of, sorry, of a regular subdivision of one of these things in the flag matroid polytopes to the category of schemes that looks like this. And so this essentially, in the language of Fluker coordinates, it kind of looks like a coordinate projection. Right, so if you're working with these spaces in terms of Fluker coordinates, this is literally going to be induced by a coordinate projection. And so given this fact, you can actually form the inverse limit over a subdivision over W vector of flag matroid strata, right? This is some now well-defined object. Okay. So let me, before saying the main theorem, let's see what this looks like in this case. So here, this is some flag matroid. This polytope or this point configuration is some other flag matroid. This one in the middle is some third one. So by this key fact, this essentially is saying that the stratum corresponding to Q vector A has a map to Q vector A B, and similarly Q vector B as a map to the common guy, right? So we have a diagram that looks like this. And so now for the punchline, which, as I said, should be on the archive soon. The theorem is that the initial degeneration with respect to this weight vector of this flag stratum, right? Initially, we were kind of interested just in the uniform case, but this works well for any flag matroid you put here. This admits a closed immersion into this inverse limit. Of flag matroid strata. Okay, so maybe this doesn't give you a lot initially, but for many cases, for many examples, especially in the when the parameters of the rank and ground set for your flag matroid are small, right? This turns out to be an isomorphism. I'm going to be a little bit vague about what I mean by this, but the point is that the usefulness of this theorem is, at least for our purposes, is when this is an isomorphism. And for a number of interesting small cases where we can compute things, it is an isomorphism. For example, so in our running example, this says that the initial degeneration of this flag upper circ, right? 1, 2, 3 has a closed immersion to this fiber product, right? It has a closed immersion to the inverse limit over this diagram. And so the inverse limit over a diagram that looks like this is literally just a fiber product. And in fact, in this case, it's an isomorphism. And you can check that this is an isomorphism sort of indirectly, right? So both of these spaces are affine schemes. And so if you know that this is smooth and irreducible of the correct dimension, and since this is a flat degeneration of your flag variety, you can easily compute its dimension, right? Just checking those 3 properties, smooth, irreducible, dimension on this side, if they all line up correctly, that'll tell you that this map is an isomorphism. And so that's what happens in this example. Right, so here's a way you can deduce that this initial degeneration is smooth and irreducible, right? It's enough to just know that this space here is smooth. Let's just say smoothness for now. So to deduce that that space over there is smooth, it's enough to know that this is smooth. And then the map from here to here, so this map here is smooth. And then you can use functorial properties of smoothness to deduce smoothness of the initial degeneration. So it's obviously ridiculous in this setting because this flag variety is cut out by a single equation. So you can just like kind of do it directly. But this is the only example that one can draw, and I feel like it really illustrates the whole point of our theorem. Right, so obviously the usefulness of this theorem is for somewhat larger examples. Great, I have some time to do the results. Some applications of this theorem.
Dan, can I ask a question in the meantime?
Yeah, what's up?
Does this, whether this is an isomorphism or not, does this coincide in any way with whether the flag Dressian is the same as the tropicalization of the flag variety, or is that independent?
So my only intuition for this comes from what happens in the Grassmannian, and it does have something to do with right, when there is a difference between the the tropical Grassmannian and the flag Dressian. So for example, like I believe if you're like working in characteristic 2, and I'm pretty sure all the theorems go through in characteristic 2 or in an arbitrary characteristic, then the inverse limit for a point in the Fano cone of the tropical GR37, that inverse limit will have dimension 13, but then the dimension of GR37 is 12, so its initial degeneration will have dimension 12. So that's an example of when this is a proper closed immersion, and it's also, but it's like, it's a weird thing, right? It's like when it's like, I don't quite have a clear picture of exactly what's going on there, but it's like, at least at the combinatorial level, right? The tropical Grassmannian sort of like cuts into this Fano cone in a weird way, right? It's like, it's not like surrounding the Fano cone as it is in the case of like characteristic 0, it rather like slices through.
Mm-hmm.
So yeah, there is some connection, but I don't quite have it pinned down.
Thanks anyways.
All right. Right, so I want to talk about applications and related results. Right, so as stated here, this is a strict generalization of the statement for if everything here was the Grassmannian, and this was proved in my PhD thesis. But sort of what's sort of a piece of news in that category is the case of GR38. So we can use this theorem to show that, and so this is joints with Dante Luber. And this appeared on the archive last week. We have that GR038 is shown. Right, remember, this means that all the initial degenerations are smooth. Right, and so this is nice. And one kind of interesting thing is that we actually show that there exists initial degeneration of GR38 that has two connected components. Right, so this is something new that doesn't quite happen for GR36 or 37 and 38. Right, so for 36 and 37, all the initial degenerations are smooth and irreducible. In 38, they're all smooth, but there's one combinatorial type that has two connected components. And then the rest are smooth, or the rest are connected. Right, so we can use this. So this again is with Luber to show that the Chow quotient of GR38 by C star to the 8 mod C star. This is the diagonal torus of PGL8. We have that this is the log canonical compactification of the moduli space of 8 lines in P2. Right, so this is also, right, so being Shun sort of gets you halfway there, and then to go from Shun to log canonical is a combinatorial check, something I was talking about earlier in the talk. And so this was actually not done by us, this was done in a paper by Schock. And so this resolves the conjecture of Hacking-Kiel and Tevlov. So now we have this checked off. Right, so their conjecture was that this Chow quotient was log canonical compactification of the analogous moduli space here, exactly in the cases 2n, 36, 37, 38. Sort of 2n was known by Tevlov, 36 by Mark Luxton in 2008, 37 by myself in my PhD thesis about 5 years ago, and now 38 in 2022. So let me maybe just state, since this was initially about flag varieties, application for a flag variety. Right, so we study concretely flags 1, 2, 3 inside of C4. So we have that this space, its initial degenerations are smooth and irreducible. And then using this, we also get that we use this to study the Chow quotient of this flag variety by this diagonal torus C star to the 4 mod C star. So this is the diagonal torus of PGL4. And so we have that this, well, it's not, it ends up not, its log canonical divisor is not ample, but it's at least smooth. And a log Crepin resolution of its log canonical model. And actually, there's a modular interpretation, something similar to this situation here. It's a little bit trickier to state, but I'll maybe refer to the paper for the modular interpretation, given that I am a minute late. But yeah, thank you for your time.